Welcome! In this session, we'll tackle an exciting problem: number of rectangles that can form the largest square. Together, we'll explore its intuition, approaches, and key insights to strengthen your problem-solving skills. Let's dive in. In this problem, you're given an array of rectangles, where each rectangle is defined by its length and width. The goal is to determine how many of these rectangles can be used to form the largest possible square. To do this, you can take any rectangle and cut it down, if necessary, to form a square where all sides are equal. The side length of the square will be the smaller dimension of the rectangle, which is calculated as the minimum of its length and width. For example, if a rectangle has dimensions 4, 6, you can form a square with a side length of 4. Your task is to find the largest square that can be formed and count how many rectangles can produce squares of that side length. Let's look at the first example to understand this better. The input is a list of rectangles with dimensions 5, 8, 3, 9, 5, 12, 16, 5. For each rectangle, we calculate the maximum square it can form by taking the smaller of its two dimensions. For instance, the rectangle 5, 8 can form a square with side 5, 3, 9 can form a square with side 3, and so on. After calculating the possible side lengths for all rectangles, we see that the largest square that can be formed has a side length of 5. There are 3 rectangles capable of forming this square: 5, 8, 5, 12, and 16, 5. Therefore, the output for this example is 3. Now consider the second example with rectangles 2, 3, 3, 7, 4, 3, 3, 7. Following the same process, we calculate the side lengths of squares each rectangle can form. The first rectangle, 2, 3, can form a square with side 2, while the others, 3, 7, 4, 3, and 3, 7, can all form squares with side length 3. The largest square here has a side length of 3, and there are 3 rectangles capable of forming this square: 3, 7, 4, 3, and 3, 7. So, the output for this case is also 3. In the third example, we have rectangles with dimensions 1, 2, 2, 1, 3, 4, 4, 3. Using the same method, 1, 2, and 2, 1, can each form a square with side length 1. Meanwhile, 3, 4, and 4, 3, can form squares with side length 3. The largest square here has a side length of 3, and only one rectangle, 3, 4, can form this square. Therefore, the output for this example is 1. Finally, let's consider some edge cases. If there's only one rectangle in the input, the output will always be 1 because that rectangle will determine the largest square, with its side length equal to the smaller of its two dimensions. If all rectangles have identical dimensions, then all of them will form squares with the same side length, and the output will equal the number of rectangles. Additionally, since the constraints allow rectangle dimensions to go up to 10 to the power of 9, the solution must handle these large values efficiently without causing performance issues or overflow errors. To solve this problem, the brute force approach provides a very intuitive starting point. The idea is straightforward: for each rectangle in the input, we calculate the largest square that can fit within it. This is determined by the smaller of the two dimensions of the rectangle, L and W, as the side length of a square cannot exceed the shortest side of the rectangle. Once we calculate this value for each rectangle, we keep track of the largest square size we've encountered so far and count how many rectangles can form a square of this size. The steps are simple: loop through all rectangles, compute the maximum square side length using min, L, W, track the largest square, and finally count how many rectangles achieve that size. Importantly, this approach has a linear time complexity of O, n, where n is the number of rectangles, since we process each rectangle in constant time. This brute force approach is efficient not only in terms of time complexity but also space complexity. It uses only a few variables to track the state, resulting in an O(1) space requirement. While the brute force method is optimal in terms of time complexity, we could consider optimizing the implementation further. For instance, using a dictionary or an array to count occurrences of square sizes might be useful in more constrained scenarios. However, for this specific problem, a single pass through the array with direct comparison suffices to meet the requirements. After evaluating these considerations, the chosen strategy is the brute force approach. It stands out due to its simplicity and efficiency. The key insight here is that the largest square side length is determined by min, L, W, for each rectangle, and by focusing on this observation, we can avoid any unnecessary complexity in the solution. The aha moment in this problem comes from recognizing that the task essentially reduces to finding the largest min, L, W, across all rectangles and counting its occurrences. This realization simplifies the problem significantly and allows us to achieve a linear time complexity with minimal overhead. When assessing trade-offs, the brute force approach may initially appear naive, but its O(n) complexity is actually optimal for this problem. More complex solutions, such as sorting the rectangles or introducing additional data structures, would only increase time or space complexity without providing any real advantages. By focusing on simplicity, clarity, and efficiency, the chosen strategy strikes the right balance, making it the best fit for solving this problem effectively. In this problem, we need to determine how many rectangles can form the largest square possible. To do this, we first need to understand that each rectangle is defined by two dimensions, its length and width. The largest square that can be formed from a rectangle is limited by its smaller dimension, which is why we calculate the square side as min, L, W. Our goal is to count how many rectangles can form a square of the largest side length among all rectangles. To achieve this, we start by parsing the input, which is a list of rectangles where each rectangle is represented by its dimensions, L, W. For example, if the input is 4, 6, 7, 3, 5, 5, these rectangles have varying dimensions. Next, we initialize two variables, max_square_side to keep track of the largest square side we've found so far, starting at 0, and count how many rectangles can form squares with that largest side, also starting at 0. Finally, we iterate through the list of rectangles and compute the largest square side for each rectangle using the formula square_side equals min, L, W. Once we calculate the square side for a rectangle, we compare it with the current max_square_side. If the square side is greater than max_square_side, it means we've found a new, larger square size. In this case, we update max_square_side to this new value and reset count to 1. Because this is the first rectangle to form a square of this size. If the square side is equal to max_square_side, we increment count by 1, as this rectangle also contributes to forming squares of the current largest size. After processing all rectangles, we simply return the value of count, which represents the number of rectangles that can form the largest square. This straightforward approach ensures that we efficiently identify the largest square size and count the rectangles that can achieve it. To understand why we use min, L, W for the square side, consider that the smaller dimension of a rectangle limits the size of the square it can form. For instance, a rectangle, 4, 6, can only form a square with a maximum side length of 4, as the longer side of 6 cannot constrain the square. Tracking both max_square_side and count simultaneously is a key optimization. By doing so, we avoid needing multiple iterations over the list, reducing the time complexity of the algorithm. This makes the solution efficient and well-suited for larger inputs. Additionally, there are some edge cases to consider. Rectangles with identical dimensions, like 5, 5, can form squares of that exact side length. If there is only one rectangle, the result will always be 1, as there's only one square to consider. Lastly, rectangles with a dimension of 0 cannot form squares, as the square side would also be 0, which is invalid. To implement this, we use a simple data structure, a list of lists or tuples to represent the rectangle dimensions, which allows efficient access and computation. The key variables are max_square_side, which tracks the largest square side length found so far, and count, which tracks how many rectangles can form squares of that size. From a complexity perspective, the algorithm is highly efficient. It has a time complexity of O(n), because we only iterate through the list of rectangles once, performing constant time operations for each rectangle. The space complexity is O(1), because we only use a few variables to store intermediate results, and no additional data structures are required. This efficiency ensures the algorithm can handle large inputs effectively. Let's go through an example to see the algorithm in action. Suppose the input rectangles are 4, 6, 7, 3, 5, 5. We start by initializing max_square_side equals 0 and count equals 0. For the first rectangle, 4, 6, we calculate square underscore side equals min, 4, 6, equals 4. Since 4 is greater than max underscore square underscore side, we update max underscore square underscore side to 4 and set count to 1. Next, for the rectangle, 7, 3, we compute square underscore side equals min, 7, 3, equals 3. Since 3 is less than max underscore square underscore side, no updates are made. Finally, for the rectangle, 5, 5, we calculate square underscore side equals min, 5, 5, equals 5. Since 5 is greater than max underscore square underscore side, we update max underscore square underscore side to 5 and reset count to 1. After processing all rectangles, the final value of count is 1, indicating that only one rectangle can form the largest square of size 5. This Python code solves LeetCode problem number 1725, number of rectangles that can form the largest square. The goal is to determine how many rectangles can form the largest possible square from the given dimensions. The solution starts by initializing two variables, max underscore side to track the side length of the largest square found so far and count to track how many rectangles can form this square. Both variables are initially set to 0. Next, the code iterates through the list of rectangles, where each rectangle is represented by its dimensions, L, W. For each rectangle, the code determines the largest square that can be formed by taking the smaller of the two dimensions, using min, L, W. This ensures that the square fits entirely within the rectangle. After calculating the square side length, the code checks if this length is greater than the current max underscore side. If it is, max underscore side is updated to the new larger value, and count is reset to 1, as this is the first rectangle forming the new largest square. If the square side length equals the current max underscore side, the code simply increments count, as another rectangle can form the same largest square. Finally, the function returns count, which represents the number of rectangles that can form the largest square side length. This implementation is efficient, with a time complexity of O, n, where n is the number of rectangles, as each rectangle is processed exactly once. The algorithm handles edge cases, such as when all rectangles are the same size or when no rectangles exist, though the latter is unlikely given the problem constraints. The solution is clear, concise, and directly addresses the problem requirements. This is the Java implementation for the LeetCode problem number 1725, number of rectangles that can form the largest square. The logic is equivalent to the Python solution, where we iterate through the array of rectangles to determine the largest square side that can be formed using the minimum of the rectangle's dimensions. We then keep track of the maximum square side and count how many rectangles can form squares of that size. Key differences include the use of primitive types, Java's math library for minimum calculation, and array indexing syntax specific to Java. Here, we are given the input rectangles as 2, 3, 3 is 7, 4, 3, 3, 3. To start, we initialize two variables, max underscore side is set to 0 to track the largest square side length we've seen so far, and count is set to 0 to keep track of how many rectangles can form this largest square. Now, we begin iterating through each rectangle. For the first rectangle, 2, 3, we calculate the side length of the largest square it can form by taking the smaller of its two sides, which is min, 2, 3, equals 2. Since this value, 2, is greater than our current max underscore side of 0, we update max underscore side to 2 and reset count to 1 since this is the first rectangle forming the largest square. Next, we move to the second rectangle, 3, 7. Again, we calculate the square side length as min, 3, 7, equals 3. This value, 3, is greater than the current max underscore side of 2, so we update max underscore side to 3 and reset count to 1. For the third rectangle, 4, 3, the square side length is min, 4, 3, equals 3. Since this matches the current max underscore side of 3, we increment count to 2 because we now have an additional rectangle forming a square of the largest side length. For the final rectangle in this example, 3, 3, we calculate the square side length as min, 3, 3, equals 3. This also matches the current max underscore side of 3, so we increment count again, bringing it to 3. At this point, we have gone through all the rectangles, and the largest square side length we found is 3. Furthermore, there are 3 rectangles that can form this square, so the output for this example is 3. Now, we take a look at the second example, where the input rectangles are 5, 8, 3, 9, 5, 12, 16, 5. As before, we initialize max_side to 0 and count to 0. For the first rectangle, 5, 8, the square side length is min, 5, 8, equals 5. Since 5 is greater than the current max_side of 0, we update max_side to 5 and reset count to 1. Moving on to the second rectangle, 3, 9, we calculate the square side length as min, 3, 9, equals 3. This value, 3, is less than the current max_side of 5, so we make no updates and continue. For the third rectangle, 5, 12, the square side length is min, 5, 12, equals 5. This matches the current max_side of 5, so we increment count to 2, as we now have another rectangle forming the largest square. For the final rectangle in this example, 16, 5, the square side length is min, 16, 5, equals 5. Once again, this matches the current max_side of 5, so we increment count to 3. After processing all the rectangles, the largest square side length remains 5, and there are 3 rectangles that can form this square. Thus, the output for this example is also 3. In this third example, the input rectangles are 4, 4, 6, 6, 2, 2, 7, 7, 8, 8. As always, we start by initializing max_side to 0 and count to 0. For the first rectangle, 4, 4, the square side length is min, 4, 4, equals 4. Since 4 is greater than the current max_side of 0, we update max_side to 4 and reset count to 1. For the second rectangle, 6, 6, the square side length is min, 6, 6, equals 6. This value, 6, is greater than the current max_side of 4, so we update max_side to 6 and reset count to 1. For the third rectangle, 2, 2, the square side length is min, 2, 2, equals 2. Since this value, 2, is less than the current max_side of 6, no updates are made. Next, for the rectangle, 7, 7, the square side length is min, 7, 7, equals 7. This value, 7, is greater than the current max_side of 6, so we update max_side to 7 and reset count to 1. For the final rectangle, 8, 8, the square side length is min, 8, 8, equals 8. This value, 8, is greater than the current max_side of 7, so we update max_side to 8 and reset count to 1 again. After examining all the rectangles, the largest square side length is 8, and only one rectangle can form this square. Therefore, the output for this example is 1. The time complexity of this solution is determined by how we process the input list of rectangles. Each rectangle is processed exactly once, and for every rectangle, we calculate the smaller side using the min, L, W, operation. This operation runs in constant time, O1. After that, we compare the computed square side with the current maximum side, max_side, and either update the maximum or increment the count. These comparisons and updates are also constant time operations. Since there are n rectangles in the list, the loop iterates n times, and each iteration involves only constant time operations. As a result, the overall time complexity of the algorithm is O(n). This linear time complexity ensures efficiency, even for larger inputs. Now, let's analyze the space complexity of this solution. The algorithm uses only a constant amount of additional space throughout its execution. Specifically, it maintains 2 integer variables, max_side, to track the largest square side length, and count, to keep track of how many rectangles can form squares of that size. Beyond these 2 variables, no other data structures or auxiliary space are used, and the memory usage does not depend on the size of the input list. This guarantees a space complexity of O1. Furthermore, because the algorithm processes each rectangle individually and independently of the input's distribution, the time complexity remains O(n) in the best, average, and worst cases. This consistency highlights the robustness of the solution. To appreciate the efficiency of this approach, let's compare it with a brute force method. A naive solution might attempt to generate all possible square sides for every rectangle and then count occurrences of the largest square side. This approach would likely involve multiple passes through the input list, significantly increasing the time complexity to O(n)2, or worse, depending on the implementation. In contrast, the current solution avoids redundant computations by determining both the largest square side and its count in a single pass, achieving O(n). To prove the time complexity mathematically, consider that the for loop runs exactly n times, with each iteration involving constant time operations like computing min, l, w, and performing conditional checks. This leads to a total of n*(O(1) operations, simplifying to O(n). For space complexity, the only additional memory used is for the two integer variables, max_side and count. The absence of auxiliary data structures ensures that memory usage remains constant, making the space complexity O(1). One of the most common mistakes candidates make is neglecting edge cases. For instance, if a rectangle has one side as 0, like 0, 5, or if both dimensions are very small, these scenarios often slip through testing. Ensuring your solution handles such inputs is crucial. Another frequent issue is the unnecessary use of division. Instead of dividing dimensions, which can lead to floating point errors or inefficiency, you can use the min function directly to find the largest square side. It's also important to keep the problem constraints in mind. For example, if dimensions can go up to 10 to the power of 9, a brute force approach that iterates through all possible values will almost certainly exceed time limits. Misunderstanding the problem statement is another pitfall. Some candidates mistakenly think the goal is to maximize the product of the sides, but the real objective is forming a square, which requires equal sides. Finally, many overcomplicate their solutions with advanced algorithms or data structures when a straightforward iteration may be sufficient. Always aim for simplicity unless the problem explicitly demands complexity. Now, let's think about what this problem teaches us in an interview setting. A key aspect is pattern recognition. The task is fundamentally about maximizing a property, in this case, the size of a square, under specific constraints. This type of problem solving is common in dynamic programming and greedy algorithms, so recognizing these patterns can give you an edge. There's also plenty of room for optimization. While a brute force approach can help you get started, discussing how to improve efficiency for larger inputs is important. For instance, sorting the dimensions or even leveraging a priority queue in certain variations might help reduce complexity. Another valuable skill is communicating the trade-offs between different methods. If one approach is faster but less readable, explain why you would use it, or vice versa. Interviewers appreciate it when candidates critically evaluate their solutions and articulate the reasoning behind their choices. Additionally, this problem connects to several related problems that can help you deepen your understanding. For example, LeetCode 221, Maximal Square, focuses on finding the largest square in a matrix of ones and zeros using dynamic programming techniques. LeetCode 1277, Count Square Submatrices with All Ones, is similar but requires you to count all possible squares, not just the largest one. If you're looking for a more advanced variation, LeetCode 85, Maximal Rectangle, involves rectangles instead of squares and often uses a stack-based histogram approach for optimization. Finally, LeetCode 11, Container with Most Water, deals with maximizing the area between two lines under constraints, which is conceptually related because it also involves optimizing dimensions. Exploring these problems can help you see the broader patterns and strategies that apply across different scenarios. Great work! We've summarized the key points and takeaways from this problem. Remember, mastering these concepts takes practice, so keep challenging yourself. Don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!